I've been at MSR for more than 10 years now and heard many hundreds of talks. One of the most memorable was Michael's previous talk here, so I think we're in for a treat. He'll tell us about streaming lower bounds for approximating max cut.
Thanks, Yuval. Thanks a lot for inviting. It's a pleasure to be here. So I will talk about streaming lower bounds for approximating max cut. This is joint work based on joint works with Sanjeev Khanna, Madhusudan, and Anaya Velankar. Okay, so this is a talk about streaming algorithms for graph problems, that is, algorithms for processing graphs using small amounts of space. So naturally, the motivation is the fact that graphs that we need to process today are large, so they often don't fit into the memory of our machines. So we want to understand the limits of computing with small amounts of memory on graphs. Okay. And in particular, we need graph analysis primitives that use very little space. We want to also understand what the limits of this is. So a very convenient model to reason about graph algorithms that use small amounts of space, and in fact the standard model for this task is the streaming model of computation. This is what we will use in this talk. So let me define it for you. In the streaming model of computation, our input is a graph. So for this talk, our input is a graph G with n vertices and m edges. Now the edges of the graph are given to our algorithm in a stream in an arbitrary order, like this. So here one should think of the vertices as known or maybe numbered 1 through n. And so these are the green dots on the slides. And the edges arrive in the stream in some arbitrary order. So the algorithm scans a list of edges given to it in a stream. And the catch is, of course, that as the algorithm is scanning the stream, it has limited memory. It is common to think of the algorithm as having about O tilde n amount of space available. So think of being able to record, say, a polylogarithmic number of spanning trees, or so store a small number of bits per vertex. But the algorithm cannot store the entire graph. Okay, good. So the algorithm gets one or more passes over the stream of edges of the graph, and then has to output the answer to the problem at the end of the day. Now, ideally, we would like to get algorithms that are single pass. So we'll look at the stream of graph edges exactly once and output the answer. And this is the setting that we will be concerned with in this talk. All right, good. So, as I said, the common assumption is to assume that the algorithm has n polylog n bits of space available to it. And in fact, this is a fairly reasonable lower bound on the amount of space to give to a streaming graph algorithm. Why? Well, there are two reasons for that. Well, first, often the size of the objects that we want to compute in graph problems are just size omega n. So think of wanting to compute a large matching in a graph, or constructing a sparsifier of a graph, or a spanner. Just the output size is omega n bits. So it makes sense that the algorithm needs omega n bits to store it throughout the process. Now it turns out, however, that in some problems, like testing connectivity, even though the output is a number, so it can be represented with log n bits, to compute the answer, one needs linear amount of space. Okay, so requiring omega n or order n amount of space is natural, but it turns out that sometimes one can go below the theta n space. In particular, a couple of years ago, we gave an algorithm for approximating the size of maximum matchings in graphs on n vertices in randomly ordered streams to a reasonable polylogarithmic factor using only polylogarithmic amount of space. So which shows that if one is interested in approximating solution cost, then it is sometimes possible to go below the linear in n amount of space. And in recent years, there have been some very nice results, getting results on graph algorithms that compute solution cost in, so to speak, truly sublinear time. So little of n, the number of vertices, as opposed to little of m, the number of edges. All right, good. So what this shows is that it is possible to approximate solution cost for graph problems in little of n space. And naturally, we would like to get more algorithms of this type and also understand the limits of this. So which problems can and cannot be solved in sublinear in n amount of space. Okay, well in this talk, we will be concerned with the following classical combinatorial optimization problem, that is max cut. So let me remind you what that is. So in the max cut problem, our input is a graph G, and the task is to find a cut in the graph G that is crossed by the maximum possible number of edges. So in particular, if the graph is a bipartite graph, then outputting the cut corresponding to the bipartition cuts all the edges. Okay. Well, what do we know about approximating max cut? Well, first, a simple observation is that a random cut in the graph, on average, will cut half of the number of edges. So that's a trivial factor 2 approximation to max cut value, max cut itself. One can do better than factor 2 using Givens-Williamson and using spectral techniques from Trevisan and Kalle and Seshadri. Okay, so this is what we know. Now, all these algorithms, however, operate in the RAM model. Namely, they need to have access to the edges of the graph in memory. So what do we know about approximating max cut in the streaming model of computation? Well, here, we don't really know that much. So there are two extremes. On the one hand, there is a trivial factor 2 approximation that uses only logarithmic amount of space. Well, as the edges are coming in, just count the number of edges in the graph, output that much by 2. It's very space efficient, but only a trivial factor 2 approximation. At the other extreme, if I have a linear amount of space, order n, or order n over epsilon squared, where epsilon is my precision parameter, then at least information theoretically, I can get a 1 plus minus epsilon approximation to max cut value simply by storing a random sample of the edge set of the graph. So the max cut value in the sample will be within 1 plus minus epsilon of the original max cut value by Chernev bounds. All right, so what we would like to understand is there anything interesting in between? And in this talk, I will present two lower bounds, ruling out some very efficient solutions to approximating max cut in the streaming model.
So what's the second? What do you mean by that?
Okay, so what I'm saying is that I can get a 1 plus minus epsilon for any epsilon. I can get a 1 plus minus epsilon approximation to max cut value in a single pass using n over epsilon squared words of space. So n log n over epsilon squared bits.
Approximation to what? Because we can't exponential time.
Exponential time, yes. Exponential time, yes. Right, so this is just the claim, right? So we're talking about streaming, it makes sense to ask information theoretic questions. So this is an information theoretic statement. Given a graph, I can just sample n over epsilon squared edges.
Oh, I see. You will then search or all.
I will just check all the cuts and yeah, good, great question. All right, good. So there will be two parts to this talk. I will present two lower bounds. And in the first part, I will start by asking a very optimistic question. So my optimistic question will be, well, could it be that there exists a non-trivial algorithm for approximating max cut value, that is an algorithm that beats factor 2, using still a polylogarithmic amount of space? Well, the answer turns out to be no, and this is our first, the first theorem that I would like to cover in this talk. So this is a result with the Sanjeev Khanna and Madhusudan. What we show is that for any constant epsilon, any single pass streaming algorithm that approximates max cut value to factor 2 minus epsilon requires root n space. And this is true even if the edge set of the graph is given in the random order. So this rules out non-trivial algorithms, even under this benign random order assumption. Okay, so unfortunately this rules out polylogarithmic space. On the other hand, this seems to suggest that about square root n space may be possible in some settings. For example, if we have polylogarithmic number of passes in the stream. Okay.
Why did you suggest that root n may be possible?
Good. So we'll see in a second that the lower bound basically shows that there is a certain birthday paradox happening there. And in particular, we will see that the lower bound we prove, in fact, is tight in certain settings. So this root n, for instance, what we will show is that in fact it's you need root n space to distinguish between bipartite graphs and graphs that are 2 minus epsilon far from bipartite in the streaming model. And even if you get quite a few samples of the edges, say m log n samples of the edges.
Your hard distributions are going to be a random graph and a random bipartite?
Yes, exactly. And those,
You can distinguish those with root n.
yes. You basically sort of pick a vertex, you run root n random walks of logarithmic length, you check mixing properties.
And a regular graphs.
Oh, good. Any other questions?
And how does that compare with number of passes? I mean, it's
So this is for a single pass. This is for a single pass setting. one can show an extension of this to the following setting. So this says that if you get the m edges in a random order, then you need root n space. What one can show is that if you get m times p IAD samples from the edge set of the graph, so you can think of this as almost p passes, not quite, but almost, then you need something like root n over p or root n over poly p. I don't remember the exact result. Okay, good. All right. So we prove the theorem by establishing, first designing a hard input distribution, and this indeed will be a random bipartite graph versus a random non-bipartite graph. Then we'll analyze the hardness of the streaming problem via a communication complexity problem, which we call the Boolean hidden partition problem. This is a close relative of a problem known as the Boolean hidden matching problem. We'll get to this in a bit. So I will define the problem and give the analysis. All right, so what is the hard input distribution? The hard input distribution is based on Erdős-Rényi graphs. There will be two cases, the yes case and the no case. Now, in the yes case, in the stream, we will get a random bipartite multi-graph. We'll have a small constant number of multi-edges with expected degree about 1 over epsilon squared. In the no case, it's a non-bipartite multi-graph with expected degree 1 over epsilon squared, so they have to be the same. Now, in the yes case, we get a bipartite graph, so max cut value is all the edges of the graph. In the no case, the max cut value will be only a 1 plus order epsilon factor above half of the number of edges in the graph. And so it will be sufficient to show that root n space is needed to distinguish between these two cases. All right, so let me remind you what Erdős-Rényi graphs are, or rather, what is the regime that we're interested in. So an Erdős-Rényi graph is a graph which is obtained by sampling every edge independently with probability p. So the probability p that we'll be interested in is below the giant component threshold, sort of a largish constant factor below the giant component threshold. So p is alpha over n for small enough constant alpha. In this regime, the graph G is a union of order log n size trees with rather high constant probability. Here's a depiction. Okay. Good. So our hard input distribution can be viewed as follows. So the input consists of about 1 over epsilon squared phases. And in the yes case, in each phase, we get a random bipartite Erdős-Rényi graph below the connectivity threshold, below the giant component threshold, as defined on the previous slide. So here's a picture. There's 1 over epsilon squared phases, and in each phase, this graph arrives, and they all share the bipartition. So we fix a bipartition first, and then every graph that arrives in the stream shares the bipartition. In the no case, one can think of this as we first sample a bipartition uniformly at random, and then and the same graph arrives. But the bipartition is resampled at every point in time. Okay. So what one can show is that in the yes case, max cut value is m, because we're getting a bipartite graph, they all share a bipartition. And in the no case, the max cut value is at most 1 plus epsilon m by 2. All right, good. So this is our input distribution. So now the question is, how does one go about proving that any single pass streaming algorithm needs root n space to distinguish between the yes and no cases? Well, a very natural way to proceed is the following. So suppose that we run our streaming algorithm on this input. So let S0 yes, S1 yes, S2 yes through Sk yes be the state of the streaming algorithm after phase k. And Sn yes, Sn0, Sn1, Sn2, etc. is the state of the streaming algorithm in the no case. So these are sequences of random variables. So our algorithm in both cases starts in some initial state, we call it 0, and then if the streaming algorithm gives a factor better than factor 2 minus epsilon approximation to max cut, the total variation distance between the two random variables, S yes k and S not k, needs to be omega 1 at the end of the day. That's the definition of distinguishing between the yes and the no case. All right, good. So one way to prove that such an algorithm requires root n space would be to set up a k-party communication problem and corresponding to the k phases and analyze this problem. However, we will proceed somewhat differently. Instead, we choose to work with a two-party communication problem because it's easier. And the way we do this is as follows. Well, we note that if we have these two sequences of random variables that start out equal and diverge in total variation distance to omega 1 over k steps, well, there must be one step, j star, call it the informative index, such that from step j star to step j star plus 1, the algorithm learns something. So these two random variables in total variation distance diverge by at least omega of 1 over k. And this is really the hybrid argument. Okay, and so basically this is where we strike. Namely, we think of splitting this sequence into two parts. And we will have two players.
I never understood why it's easier to understand such an argument in negation. Why not just prove that at every step it's at most 1 over k, so by the triangle inequality, I mean, it's a little of 1.
So that's exactly it.
I know, it's always been confusing to me why the hybrid inequality is called, the triangle inequality is called hybrid.
Oh, no, but I think it's a bit different, right? Because there's the other interesting part, right? The interesting part comes later in the sense that what we will do is we find the informative index, which is really just the triangle inequality, right? But there's one other observation that says that you can run your algorithm on sort of the first j phases of the yes case, and then give it a step that doesn't entirely check out. That is, you run it on the yes case, but then you give it one no step and one yes step. So I think this is really the hybrid argument, in a sense. It's not quite the triangle inequality. Anyway, I'll get to this in a second.
Okay, this is triangle.
Okay, yeah.
Let's just change one thing at a time.
All right. Good. So we'll split the stream into two parts. To the left of j star and to the right of j star. So now Alice will have access to the left part of the stream, and in fact, if Alice has access to the left part of the stream, she might as well just know the bipartition x, because if she observes a lot of these graphs, she can learn the bipartition. So our two-party communication problem will work like this. So Alice has a bipartition x, and Bob will have a graph G. One of these graphs. So in the yes case, his graph will be consistent with the bipartition. In the no case, it will be very inconsistent with the bipartition. I'll be more precise about this in a second. Okay.
You guys call the triangle the Lindbergh method, right? Also, it's not so. Nobody's free of it.
All right. Good. So this is our setting. So Alice will hold the bipartition, and then Bob will hold either a graph that's consistent or not consistent. Okay, so this is the intuition. Now let me define the Boolean hidden matching problem precisely. Rather, we call it the Boolean hidden partition problem. And the Boolean hidden partition problem, or BHP for short, is this. So Alice holds a binary string x, which can be thought of as encoding a bipartition of the graph. And here are the nodes of the graph. So this is a string, so there's a binary label for each vertex. And Alice compresses the string into a single message m, sends this message to Bob. Bob has a graph G on the vertex set n, and together with the graph G, Bob has labels. So the edges of his graph are labeled. Labels are called WE, so each edge has a binary label. Now this is very similar, or rather this is an extension of the Boolean hidden matching problem of Gavinsky, Kempe, Karenides, and Raz. Now in the yes case, the labels that Bob sees on his edges are consistent with the bipartition that Alice has. So the label on the edge UV is just XU plus XV mod 2.
What's the problem? What is BHP?
I'm not completely done defining it, but sort of we have this. I haven't told you what the question is. Okay. The question will come at the end. Good. So there's the question is to distinguish between the yes and no cases. Right, but in the yes case, Alice has this binary string. Bob gets a graph with labels on the edges, and in the yes case, the labels are consistent with Alice's bipartition. So for each edge UV, what you see on the edge is the parity of XU and XV. And in the no case, so here's an example. So 1 plus 1 is 0. And in the no case, the labels are just uniformly random. So the labels that Bob observes have nothing to do with Alice's bipartition. Okay, so now the question is, what is the smallest possible size of the message that Alice must send to Bob so that Bob can announce whether or not they are in the yes case or in the no case? All right, good. So this is the Boolean hidden partition problem. we will use a distributional version of this problem, so let me define the distribution for you. And the distribution is as follows. Well, Alice gets a uniformly random string, x in 0, 1 to the n, and Bob gets a graph G sampled from the Erdős-Rényi distribution with probability alpha over n for small alpha, so way below the giant giant component threshold. Now we're in the yes case independently with probability 1/2, in the no case independently with probability 1/2. Okay, so now, in fact, the first thing to note is that this problem has a trivial root-n communication protocol. Well, this is just because Bob has a linear number of edges, and they are random. So if Alice simply sends the values of the first root n bits, or for that matter, any root n bits, with constant probability, one of Bob's edges will land with both endpoints into Alice's set. So Bob will know what xa and xb was, and he will know the label. He'll just add them up and check which of the two cases they're in. Okay, so there is a root-n communication protocol, and we'll see that root-n communication is actually needed.
Sorry, what was the, I still remember the yes. What was the no instance?
The no instance is when the labels that Bob observes are just uniformly random. Right? So in the yes case, Bob...
Okay, so it's bipartite versus random graph, basically.
Yes.
Alice is a cut. And
Yes.
Bob is a cut.
Good. All right, so this is the problem. So before I give the analysis of the problem, let me tell you how this relates to max cut. I'll give you the reduction. So what we show is that any single pass streaming algorithm that achieves a 2 minus epsilon approximation to max cut value with high constant probability gives advantage omega 1 over k, where k is the number of phases, it's epsilon squared roughly, over random guessing for Alice and Bob. All right, and so now I get to come back to the hybrid argument, and the reduction works as follows. So Alice holds a bipartition x in 0, 1 to the n. So in particular, she can generate the first J star stages of the yes case for our distribution. She runs the streaming algorithm on the first J star stages and ships the content of its memory to Bob. Now Bob has a graph G, but it's not quite the graph that we want. Bob looks at his graph G with labels on the edges and simply keeps those edges that have 1 written on them. Now, and call this graph G prime. So in the yes case, the graph G prime is a random Erdős-Rényi graph consistent with Alice's bipartition. In the no case, it's just a random subsampling of his graph. Okay, so this is the reduction. All right. Good. So this shows that if we are able to prove that the Boolean hidden partition problem requires root-n communication, then approximating max cut value to better than factor 2 requires root-n communication as well. So let me now tell you how the communication analysis goes. So analysis of the Boolean hidden partition problem. Okay, so this is fairly similar to the analysis of Gawinski, Kempecker, and Lissen-Raz. But I will still go into some details because this will inform our development in the next part of the talk, where we do better than the Boolean hidden partition problem. So here we'll see where one needs to improve in order to go from a root-n bound to an omega n bound that we obtain. All right, so we want to prove that the Boolean hidden partition problem requires root-n communication. Now the first observation that one makes is that for this purpose, it suffices to consider the yes case only. Now remember that in the yes case, Bob's labels on the edges were exactly consistent with Alice's bipartition x. So in particular, the labels W that Bob receives can be written as M times X, where X is the bipartition, and M is the edge incidence matrix of Bob's graph. So what we would like to show is that in the yes case, if Alice's message is small, then the distribution of M times X conditioned on Alice's message is close to uniform in total variation distance. Right? Because this is what is happening in the no case. In the no case, the distribution of labels, W, that Bob gets, is completely uniform. We want to prove that if communication is small, then in the yes case, the total variation distance to uniform is small.
What was proved earlier about it?
These authors who studied this BHP.
Say again?
What was proved earlier about this BHP problem?
BHP problem is what we defined.
I mean, you showed you put this problem up there, the hidden matching problem, and you.
So the distinction between the Boolean hidden partition problem and the Boolean hidden matching problem is that in the Boolean hidden matching problem, Bob's graph is just a matching. So as I said, the analysis that we will see for the Boolean hidden partition problem is fairly close to the Boolean hidden matching problem itself. And in fact, Gavinsky, Kempe, Kernidis, and Raz, they did prove the root and bound. So we'll basically see the proof. The only difference is that you have to change the graph. Go from a random matching to a random order for any graph. And then later I will show how to improve on this. Okay, good. So this is what we want to show. Conditioned on Alice's message, the distribution of mx is close to uniform. So it turns out that the following way is very convenient. The following way of thinking about this is very convenient. So initially, x was uniform on the Boolean cube. Now, conditioned on Alice's message, the bipartition x is uniformly random on some subset of the cube. So this is the red ellipse shown on the slide. Furthermore, if Alice conveys s bits of information, then the size of this set A is about 2 to the n minus s. It occupies a 2 to the minus s fraction of the cube. So let f be the indicator of this set A, that is the typical message. What we want to show is that the following distribution is close to uniform. So for each z, where z is a candidate labeling of the edges of Bob's graph, let p sub m of z be the probability that Bob observes those labels, conditioned on Alice's message. So when x is uniformly random in the set A. We want to prove that this distribution is close to uniform in total variation distance. So what Gavinsky, Kempe, Kernidis, and Raz showed is that it's convenient to write this distribution in the Fourier basis. So one writes the distribution Pm in the Fourier basis, and well, our task now is to show that this is close to uniform. Well, in order to do that, it suffices to show that most of the Fourier mass of this Pm hat is on the constant term. Or rather, that the amount of mass on the non-constant terms is small. So we want to show that this quantity is small. Now, the analysis of Gavinsky, Kempe, and others shows the following bound. The total variation distance between the distribution of labels on Bob's graph, on the edges of Bob's graph, and the uniform distribution can be bounded by the following quantity. So let me parse this quantity for you. So there's some very natural normalization factor that I won't get into much. But apart from that, what we observe is that this is a sum of the squares of Fourier coefficients of the function f, the indicator of Alice's typical message. Except we're summing over non-zero elements of the spectrum, and not just over the entire spectrum, but rather over special elements of the spectrum that can be written as m transpose s. All right, well, what does it mean that an element of the spectrum, V, can be written as M transpose S in our setting? Okay, so this V is just a subset of vertices. And our graph G was an Erdős-Rényi graph. It's a union of small trees. Okay. Well, it turns out that one can show the following: that M transpose S equals V just means that the vertices in V can be matched up by paths in our graph. Now, this is only because the graph is a union of trees. So in particular, just to give you a simple example, if V is a weight 2 Fourier coefficient, so we're interested in 2 vertices, these are the 2 red vertices. So this particular V can be written as a sum of indicators of edges in the graph.
Every graph is a union of trees in the sense that
You must mean here, so I'm confused.
Well, the general condition is this, right? So you have, so what is this M transpose S? So M was the edge incidence matrix of our graph. And I'm asking the question, well, given a Fourier coefficient V, which is nothing but a set of vertices in the graph, when can one express V as M transpose S?
and this is mod 2.
This is all mod 2, yes. So in general, this is exactly the question. You add up edges, think of indicators of edges, and you want to get a graph that is even degree everywhere except at the vertices of V. So in particular, if your graph is a union of trees, this simplifies substantially. So there's very natural intuition. If you have, for example, weight 2 Fourier coefficient. So you're asking the question, conditioned on Alice's message, how much does Bob know about the parity of x1 through x1 plus x3? This is given by, Bob either knows nothing, or he knows, he has some amount of information, depending on whether or not these two vertices can be, belong to the same component.
So you'll be using the fact that the Erdős range and the graph is in your range is almost a union of trees.
It's with the high constant probability, it is a union of trees.
I don't know what it means to be a union of I mean, my issue here is that what I see. Okay, good. So this is because this is just from one of these however many phases I see. This is not the whole full graph. This is only one over. This is only okay. Fine. Exactly. This is only one of the phases. That's
yes.
why it's That's why it's such a simple graph. Okay.
Yes.
I mean, of course, the union of trees is bipartite. So it would be weird if your hard example for the non-bipartite case was bipartite. But now I see it. So it's one of the graphs and one of the phases.
Yes, exactly. So this is exactly the reason why we're doing this reduction of sort of k phases to one. Alice. Good. All right. Good. So this is really what it means for a Fourier coefficient v to show up on the right-hand side. And for our setting, if we have a weight 4, say, Fourier coefficient, this just means that it can be partitioned into pairs, and the pairs can be matched up by paths. In other words, it just needs to intersect every connected component an even number of times.
Sorry, I keep asking questions. In the matching case, this is just some kind of noise, some kind of like. So, like, suppose that M was a matching.
Yes. Then the condition is just that you have a set of vertices. The random matching M needs to induce a perfect matching of your subset. So your V needs to be perfectly matchable by edges of your random match.
So what I'm saying is then the Fourier equation just becomes the. I'm wondering how the Fourier equation transforms under this. That's what.
No. So what this basically says is that you have this function f, and this random graph sort of samples its spectrum. How does it sample its spectrum? You pick an element of the spectrum and ask the question: well, does it contribute to the total variation distance to uniform? And, with what probability? It contributes with exactly the following probability. Given, say, a coefficient v of weight, say, 2k, what's the probability that your random matching M induces a perfect matching of v? Namely, you have to be able to match up the vertices. Right? So it's a little bit simpler. Sort of the original setting is a little bit simpler, but then the setting with Erdős range graphs is morally the same situation.
Right, but the answer to that question was exponentially small in this weight in the size of the character.
Great. That's the next slide.
That's what I was saying. It's the Beckner operator in the case of matchings, at least. If you take this function and you replace the.
Okay. So maybe this will answer your question. Good. So then you ask the following question: What is the probability that a weight k coefficient appears on the right-hand side? Well, it's exactly, well, not exactly, it's n to the minus k by 2, at least for constant k's. For non-constant k's, you get some sort of a binomial coefficient. Okay, good. Okay, this is great. So what this shows is that you have the spectrum of f, and the spectrum is sampled, and the elements of the spectrum that are higher weight are sampled more aggressively. So, and the analysis of Gawinski and others, and our analysis of Boolean hidden partition problem, proceeds by saying the following. Well, if one can show that the amount of Fourier, the L2 squared mass on various levels of the spectrum doesn't grow too fast, then these two things imply a good result. And such a bound can indeed be proven. So this is a lemma from Gawinski and others. If you have a indicator function of a subset A of the Boolean cube that occupies at least a 2 to the minus s fraction of the cube, then the amount of L2 squared mass on 2k weight coefficients can be bounded by basically order s choose 2k. Okay. All right. So note that one grows as n to the decays as n to the minus k by 2, and the other as s to 2k. All right. So what is the intuition? For intuition, let's just plug in k equals 1. So what this says is that if I have an indicator function of Alice's typical message, and Alice sent S bits, then the amount of information that Alice conveyed about the parities, the size 2 parities, is about S squared. So with S bits, I learn about S squared parities. Now this makes sense. This is exactly the birthday paradox. If Alice sends the first root n bits, I learned about n parities. That's why Bob can solve the problem. And indeed, what this means is that, so this is a lower bound, because now we can say that the contribution from k equals 1 to the right-hand side is s squared over n by this token. And so if the amount of bits that Alice has is less than root n, then the total variation distance is indeed small to the uniform distribution. All right. So this is really a lower bound that matches the birthday paradox. Great. Okay, on the other hand, we would like to, this concludes the analysis, really. We get that 2 minus epsilon approximation to max cut requires root n space in the streaming model. On the other hand, we would like to prove this bound is not tight. We would like to prove a better bound. So in the next part of the talk, I will show how to improve on this analysis. And one thing to note from here is that this lemma from Gavinsky and others that bounds the growth of Fourier coefficients, the amount of L2 squared mass of Fourier coefficients, is pretty tight. You can't really improve it. It's tight for the hypercube. So in order to get a better bound, we will need to do something else. So now let me show you some of the main ideas. I think I have only 20 minutes now. 20. Now this should be good enough. Okay. 24. Oh, I have a lot of time. This is excellent. All right. Good. So note that this is the flavor of the analysis that we will use for a stronger result. Nevertheless, we will try to do better. Now, the problem is, though, that in order to do better, one will need to set up a different communication problem, and one will need to use stronger properties of the Fourier transform of this typical message. Because this lemma from Gavinsky and others, which follows from hypercontractivity and bounds the amount of L2 squared Fourier mass on various levels of the spectrum, is tight. And indeed, for example, if you think of a coordinate subspace, that is, if Alice sends the values of the first S bits, and if you look at the typical message, then the Fourier transform of that typical message will basically be a constant, say 1 with proper normalization, actually as here, if this Z is a subset of the first S bits. So you really get about S choose K, or the S choose 2K. All right. So now let me show you how to do better. What we'll prove is that 1.00001, so some 1 plus omega 1 approximation to max cut value, requires omega n space. And this is joint work with Sanjeev Khanna, Madhusudan, and Amir Velinger. What we'll show is that there exists some constant epsilon star, such that any single-pass streaming algorithm for approximating max cut value to factor 1 plus epsilon star requires omega n space. Okay. And unlike the previous result, we're not aware, this result wouldn't actually extend to this setting where you get a logarithmic number of passes, so to speak. At least we don't know that it would. All right. So before I give the proof, though, let me give you an outline of where this is situated in the grand scheme of things. So we would like to understand the approximability of max cut in a small space. And the first very optimistic question that we asked is, could it be that there's a strong algorithm, say a better than factor 2 approximation with polylogarithmic space? Now, it turns out that the answer is no, that any, as we just saw, any better than factor 2 approximation requires root n space. Now, using similar techniques, namely the Boolean hidden hypermatching problem, one can show that 1 plus minus epsilon approximation to max cut in a single pass requires n to the 1 minus order epsilon space. Now, this lower bound, and I will not talk about it, leaves open the possibility of, so to speak, an approximation scheme. Perhaps for every approximation factor alpha between 1 and 2, there exists a space-bound beta between 0 and 1, such that an alpha approximation can be achieved in n to the beta space. So this would be consistent with this state of affairs. Now, what we show in this part of the talk is that the answer is no. There exists some alpha, close enough to 1, beyond which you need linear space. All right, so where does this leave us? Well, this leaves us with the following possibility, which would be very interesting. So perhaps there exists some approximation factor alpha star and some space-bound beta star, which is strictly less than 1, such that an alpha star approximation can be achieved in beta star space. This would be very interesting. OK, good. So now let me show you the omega n lower bound for very good approximations to max cut.
So can you go back? I mean, so why does the 1 plus epsilon already give you the result you're talking? Because if I set epsilon to be pretty close, you're saying that okay, that's an.
You would need epsilon 1 over log n to make it omega n. So for any constant epsilon, this is n to the 1 minus. I want to make the exponent here 1. Sort of qualitatively, though, it's really asking the question, is there an approximation scheme? Or OK, good. And yeah, and interestingly, one actually needs new techniques to do.
Yeah.
All right. Good. So now, as before, of course, we will establish a hard input distribution on max cut instances. And similarly to before, we will have 2 cases, the yes case and the no case. In the yes case, we will get a random bipartite graph, but it will not quite be the Erdős-Rényi graph. It will be a somewhat carefully crafted random bipartite graph with about a constant degree. And similarly, in the no case, a non-bipartite graph with constant degree. We'll ensure that there's a max cut value gap between the yes and no cases and prove that any little of n space algorithm cannot distinguish between the yes and no cases. So one needs to to have omega n space. OK. So this requires a new communication problem, which we call the implicit hidden partition problem. So I'll talk about the problem, talk about the reduction to max cut, rather from max cut, and then give the analysis. OK, so in the implicit hidden partition problem, there will be a number of players. It's a t-player communication problem. Each player receives 2 pieces of input, a graph G on the vertex set n, and labels W on the edges of the graph. So here, player 1 receives a graph G1. Here is the graph G1 with 3 edges, and labels W1 on the edges, 0, 1, 0. Now, the graph G1, so the graphs will be public inputs. So as soon as the player receives the graph is posted on a public board for everyone to see. The W's, the labels, are private inputs. So the player compresses the W's into a message and posts the message on a board. So we are on this blackboard model. The player posts his message on a board, and everybody else later sees this message. Good. So there are T players. And the tth player, again, gets a graph GT, which is immediately posted on the board, labels WT on the edges, and posts a message MT. The tth player must announce the answer. Are we in the yes case or the no case? Let me tell you what the question is. The tth player has to say what the answer is. The question is this. In the yes case, the labels that the players observe are consistent with some bipartition of the vertices of the graph. So there exists an x such that for each t, Wt is just mt times x. So mt is again the edge incidence matrix of the tth player's graph. So in the yes case, the labels are consistent with some bipartition, and in the no case, no such partition exists. Okay, good. So what is the distribution that we will use? Again, we will choose a random partition x. X is uniformly random in 0, 1 to the n. And in the yes case, all the labels that the players observe will be consistent. So Wt is just mtx. And in the no case, as before, the labels are uniformly random. OK, good. So I haven't quite finished defining the distributional version of the problem because I have to tell you how many players there are and what the graphs are. So there will be 3 players, so T is 3, and the graphs are somewhat carefully crafted. So player 1 will get a perfect matching. This is the red matching shown on the slide. So player 1 is the red player, gets a red perfect matching. Player 2 will get a random nearly perfect matching. I will not go into the details of the distribution, but for example, there won't be any cycles in these two matchings. So this is the blue matching. Okay, so since the matching is random, this is a reasonable depiction of the matching, but in fact, a union of two matchings is basically a Hamiltonian cycle. And in our case, this is a Hamiltonian cycle cut into sufficiently long, but still constant size paths. There are no cycles. This is player 2. And player 3, finally, gets an Erdős-Rényi graph, G3. This Erdős-Rényi graph will be slightly below the giant component threshold.
So union matches could be a bunch of cycles.
He means in this model that you will not have.
Yes, I will not get into the details of the distribution, but we basically ensure that there are no cycles. It's a random matching, but there are some dependencies.
In fact, this is probably why you cut the blue player's edges, right? I mean, if you chose a random matching with no cycles, that would be quite difficult to analyze.
Yeah, it would be tricky to analyze. Basically, what we do is we choose the first matching, and then then take the edges of the first matching, partition them into large enough constant-size groups, and then ensure that the second player's matching connects these groups into paths. So there's a carefully defined distribution, but it's very similar to just two random perfect matches. Okay, good. So this is the distribution. Now let me tell you what this has to do with max cut, that is give the reduction, and then talk about the analysis of the communication problem. So the reduction to max cut is naturally quite similar to what we have seen before. So suppose that our players have access to a streaming algorithm with small space that gives a very good constant factor approximation to max cut. So then the tth player simply generates the graph G prime T by keeping those edges of GT that had 1 written on them, and feeds the graph GT prime to the streaming algorithm, then posts the content of its memory on the board. Now, in the yes case, by the definition of our problem, the labels are consistent with some random hidden bipartition X, so we get a bipartite graph. In the no case, the labels are uniformly random, so what we get is a subsampling of the union of the three graphs G1, G2, G3 at rate 1/2. And now what we show is that there exists a max cut gap. So in the yes case, the graph is clearly bipartite. Whether or not the max cut value is 1 minus omega 1 below m, in the no case is not obvious, but it turns out to be true. So what we show is that if G1 is a perfect matching, G2 is this appropriately defined nearly perfect random matching, and G3 is an Erdős-Rényi graph very close but slightly below the giant component threshold, then if we subsample the edges of these graphs at rate 1/2 and take the union, this graph is omega 1 far from bipartite. And I will not get into this analysis, but the analysis at a high level is similar to, say, the analysis when one wants to prove that the Erdős-Rényi graph, just slightly above the giant component threshold, is omega 1 far from bipartite. So this has to do with, say, the way the analysis goes is by showing that there exists a giant component, for example, in the union of these three graphs. All right, good. So this is the reduction to max cut. Now, how do we analyze the problem? How do we show that this implicit hidden partition problem requires a linear amount of communication? Okay, so we have the three players, player 1, player 2, player 3, and they receive their graphs G1, G2, G3 together with the labels W1, W2, W3. Well, one very natural way of analyzing this problem would be to say, well, let's just add some player 0 who holds the bipartition X explicitly. And this is exactly what we did in the first part of the talk. This was Alice, who knew the bipartition. And then, as we showed in the first part of the talk, basically the communication between the T players is dominated by the communication between player 0 and one of the other players. So then it's a two-party communication problem. Now, however, the problem is that one can't really prove a better than root n bound using that approach. So the main innovation in our work is to do away with player 0. So in our analysis, the random bipartition X is never revealed to any of the players explicitly. And hence the name, it's the implicit hidden partition problem. Okay, good. So now this is what we prove, that any one-way protocol with sublinear in n communication achieves sublinear advantage over random guessing for our problem. So the main tool will be Fourier analysis, and in particular the convolution theorem, plus some graph-theoretic considerations. Okay. So it will come in 2 slides. Good. So let me give you some of the main ideas. So as before, it turns out that it suffices to only look at the yes case and prove that what the players observe in the yes cases looks like the no case. And furthermore, it suffices to look at the setting when players 1 and 2 have spoken and analyze the distribution of X conditioned on the messages from player 1 and player 2. Okay. So player 1 transmits some information about the random bipartition X, which constrains the bipartition X to some set A1, some subset of the cube. Player 2 transmits some information about X, which constrains X to be uniformly random in a subset A2 of the Boolean cube. Both subsets are reasonably large with reasonably large probabilities. They occupy about a 2 to the minus s fraction of the cube. So let f1 be the indicator of a1 and f2 be the indicator of a2. So conditioned on the messages m1 and m2, X is uniformly random in the intersection of these 2 sets. So what we want to understand is the indicator of a1 intersect a2. Now that's the product of the indicators of f1 and f2. And now furthermore, what we need to understand is the spectral properties of this product, f1 times f2. Even to be more precise, what we need is to prove a stronger bound than what follows from the lemma from Gavinsky and others, what follows from hypercontractivity, on the amount of L2 squared Fourier mass on weight 2k coefficients of this function. So let me say this again. So conditioned on the 2 players' messages, our bipartition X is uniformly random in f1 times f2. We would like to reuse the analysis of Gavinsky and others, but we want to get a n bound as opposed to root n. So for that, what we would like to do is prove a tighter bound on the amount of L2 squared mass at various levels of the spectrum. So for example, suppose that we're interested in the L2 squared mass on coefficients of the spectrum of weight 2k. So what would follow directly from this lemma of Gavinsky and others, from hypercontractivity, is that this L2 squared mass is at most order s over k to the 2k. And that's exactly, but we want to replace the 2k and the exponent with a k. And that's exactly the difference between root n and n. Okay, so how do we get this? In order to achieve such a bound, of course, we need to use some special properties of f1, f2. Because as I mentioned before, the bound from Gavinsky and others is tight for subcubes. Okay, and so the special properties that we will use is exactly the fact that our players never get access to the partition X explicitly. Players only access X via mj times X. So player 1 observes m1 times X and compresses the parities over edges of m1, and player 2 compresses m2 times X. So what this means is that if we look at the indicators f1 and f2, then their Fourier transform is supported on the edges. And in fact, it's a very simple observation to make that the functions f1 and f2 satisfy the stronger spectral properties that we need. The exponent here is reduced by a factor of 2 simply because one edge contains 2 vertices. So this part is very simple. And intuitively, what this means is that because the players transmit informations, get information about X via parities over edges, and with space S, we can only learn about S pairs of vertices, whereas before, if we had access to X explicitly, with space S, we would get S squared pairs. Okay, good. So this is a simple observation, but now, of course, what we need is a similar analysis for the product F1, F2. But now the Fourier transform of a product is the convolution of Fourier transforms. This is the convolution theorem. The Fourier transform of F1 times F2 is just F1 hat convolved with F2 hat. And this is exactly what we use to achieve the bound for the distribution of X conditioned on player's 1 message and player 2's message. Let me just give some of the intuition behind this. And the intuition is as follows. So suppose that, so this is our graph. It's a Hamiltonian cycle cut into sufficiently large constant size pieces. For instance, and suppose that player 1 and player 2 have spoken. So player 1 transmitted some information about parities across the red edges, player 2 about the parities across the blue edges. And we want to know, well, conditioned on the 2 messages, how much does player 3 know about parity of XA plus XD? Well, player 1 transmitted some information about the parity of XA plus XB plus XC plus XD because of this edge and this edge. Then player 2 transmitted some information about the parity XB and XC because of this edge. And so these are combined to give the parity of XA plus XD, and that's exactly what the convolution theorem makes precise. Okay, just one short technical slide. So basically what we would like to prove is that if we look at F1 times F2 hat squared, if we sum these quantities over weight 2L Fourier coefficients, then this is not too large. But in general, by the convolution theorem, we can see that fairly high weight Fourier coefficients of F1 contribute to the sum. And this is worrisome because we know that the sum of squares of high weight Fourier coefficients of F1 is fairly large. It's much larger than what we need. But it turns out that there is a multiplicative term here that is small for k larger than L. So there's not too much mass transmitted from high weight coefficients to low weight coefficients. And the intuition for this is as follows. When player 1 chooses which edges to transmit information about, player 1 doesn't really know what the blue edges will be. So the probability of it's unlikely that very long paths will form in this union of 2 matchings. And this is the intuition for why contribution from higher weight coefficients to lower weight coefficients is small.
Here you're flipping 2L bits. So in the right hand side, you're flipping
K minus L rather. So K is large. So here
you're summing over V's of size 2L.
yes, but W is size 2K.
Yeah, but what I perhaps more important, I think, for this than, but the point is you're adding noise here at some rate. I think you think about this in a different way of just flipping every bit with probably 2L over N. Okay, never mind. I don't know why you're shaking your head. You know how the hyperconductivity theorem is proved?
Yes.
Okay, so then.
But this is not. This is different.
Well, you want to show that it is small.
Yeah.
Yeah. So okay. So what's the analytic proof that this is small?
Oh, what is
It
this?
seems that you can just write down the Fourier coefficients of this in terms of the Fourier coefficients of F2.
It will be some linear combination, right? So the Fourier coefficients of F1 times F2 is just the product of Fourier coefficients of F1 and F2.
I'm talking about the right hand side. You said small for k greater than L.
Oh, okay, uh-huh.
So I'm saying, so you want to prove this is small for k greater than L.
Yes. Yes.
So how do you prove that?
Yes, okay, good. So, so that's the part that I'm basically skipping. But so what does this really mean? This W plus V. So let's see. Right. So this basically says the following. So let's consider an example. Suppose that L is 1. So our V is weight 2. So sort of we fix up front 2 coefficients. Imagine player 1 knows the red matching. It's fixed. And then we fix A and D. And we don't yet know that there's this blue edge here, right? And we want to know what will be the Fourier coefficient of F1 times F2 of A union D. right? This Fourier coefficient will only be non-zero if the edge AB and the edge CD will end up in the same connected component, right? So this is really what is happening here. So one needs to use the randomness of the second matching. Okay, I'm running out of time, so maybe we should take it offline. Good. Let me just summarize. This is the last slide. What I showed is a Fourier-based analysis that gives omega n spacebound for 1 plus 0.0001 approximation to max cut. There are some very nice open problems. And one of them is to find out whether or not there exists a sublinear time algorithm for max cut, which is better than factor 2. This would be very exciting. Or maybe one can get a better analysis. So one natural approach to better analysis would be to learn how to convolve, to go to a multiplayer setting. So here we use 3 players. So we get some 1 plus omega 1 gap. And if we could use 1 over epsilon squared players and analyze the convolution, we may well be able to prove that 2 minus epsilon requires omega n space. Thank you.
So Michael is here until
Thursday.
You have time for one more question. Otherwise,
Yeah, so it's so here's one interesting lower bound that's suggested by this, which is if you look at these Shirley-Adams relaxations for approximating max cut, then I made some suggestion a few years ago that maybe you could get sort of better than a factor 2 approximation using like sub-exponential time. But this suggests that maybe you can prove a lower bound, at least that you need sort of n rounds of Shirley-Adams to get some 1 plus epsilon approximation.
Oh, I see. Oh, this is very interesting.
Because those Shirley-Adams correspond to basically things that are allowed to query n edges of the graph and then do something based on them. So it's actually some part of the model is stronger, but some part of the bound would actually be weaker because here you're doing something information theoretic, and there you're allowed to, yeah. So
it sounds very interesting. Okay.
And what is known for min cut in streaming model?
For min cut, omega n is needed, right? Because connectivity needs omega n, and that implies distinguishing between 0 and at least 1. Yes.
No, I mean upper bound ones.
Oh, order n, n polylog n. Yeah. So if you don't care about polylogs, then that's.
And polylog n and optimal.
So omega n bits are needed, and n log n bits suffice. Yes, n log n bits suffice. You can just store a spanning tree.
okay, I think we're gonna.
Oh no, actually, n polylog n bits suffice. Yes.
We're gonna thank Michael again, and I think that's enough time.